Disclaimer before we start this video, I would like to remind everyone watching that I am not a chemist and I am not a physicist. And the title of this chapter is The Chemical Basis of Life. And while the topics we will be discussing, I can easily go into much more depth with, that is not relevant for the purposes of a very general, very intro level biology talk. All right, with that out of the way, please enjoy the following few minutes. Hello and welcome back to another installment of Biology for Beginners. As always, I am your host, Morgan. Today our topic is water. So before we really dive into the water content here, I just want to remind you guys of hydrogen bonds, since they are probably the most important bond when it comes to the properties of water. Now, a hydrogen bond is just a weak chemical bond between the weakly positive hydrogen in a polar covalent bond and a weakly negative atom in another polar covalent bond. And like I said, these are going to be the key to the properties of water. Now, a big thing about water is that water is sticky. And how water is sticky is because of cohesion and adhesion. Now, cohesion is the sticking together of molecules of the same kind. So in water's case, one water molecule sticking to another water molecule. And adhesion is the attraction between different kinds of molecules. So like a water molecule sticking to another kind of molecule. And this will be done through those hydrogen bonds we mentioned in the last slide. And when you put things like cohesion and adhesion together, you can get what is known as surface tension, which is when you see in this photo here, the glass with the water bubbling up at the top because it's clearly overfilled, but the water is not flowing out. That little bubble happens because of the surface tension of the water has not broken, so it's holding it there, or you wouldn't really think it would. This is also why dew droplets and rain droplets have their very specific shape. And in the other photo here, we see a water strider effectively walking on the water. But if you look at the circled portion, you can see the little divots where the water strider is actually making contact with the surface of the water. However, the insect is not breaking that surface tension, so the only thing that's happening is a little bend in the surface and the strider being able to sit on top. Water has a fairly interesting interaction with heat. Now, heat is the thermal energy transfer from one body of matter to another, and thermal energy is just the energy associated with the random movement of atoms and molecules. So every single thing is moving at least a little bit. Even this phone, the atoms and molecules inside it are vibrating at least on some level, even though we cannot perceive it. To us, it's still a solid. Now, temperature is the measure of that average thermal energy in the atoms and molecules in a body of matter. So degrees, Fahrenheit, Celsius, and then depending on how far you study science, you'll learn about Kelvin, which is another fairly standardized scale of temperature, but we're not going to get into it here. And the important thing to know about this temperature concept is that at a higher temperature, there's going to be more molecule and atom movement. So liquids can move to gases because gases are a bit warmer when you're breaking from liquid to gas. The atoms, the molecules, they're moving more than they were in liquid form. And then as there's a lower temperature, there's going to be less movement. And as I said, with one particular substance, if you go up from cooler to warmer, you'll go from solid to liquid to gas. Water is fairly unique in the way it can interact with heat. This is because water contains a lot of hydrogen bonds, and as you add heat, those bonds will break. And because of the amount of hydrogen bonds in the water, it can absorb a very large amount of heat. And this can create an evaporative cooling effect where as the molecules at the surface start to warm up, those bonds are broken. They then escape the liquid form and move into gas, but they do leave behind an overall cooler surface since the heat then escapes as well when those bonds are broken. And this is why sweating makes us cooler, because the water in our sweat evaporates, leaving behind a cooler surface, or our skin in that case is the cooler surface. The large bodies of water in coastal areas are also what makes their climate a little bit moderate compared to more inland, because in the summer, the oceans will absorb a large amount of heat from the air, which then makes the land around them a bit cooler. And then in the winter, as the air cools down, that heat is then re-released back into the air, which makes the overall surrounding area a little warmer. The next interesting property of water that most people tend to overlook is the fact that ice floats. And so in general, as you're going from liquid to solid, the water cools down, then the hydrogen bonds stabilize, which it's not to say that liquid water doesn't have hydrogen bonds, it's just that they're unstable bonds that are constantly breaking and reforming from molecule to molecule. So these stable bonds in the solid crystals kind of hold each other at arm's length, and they don't break spontaneously and reform. And so because these molecules are now they're apart by these bonds, the ice has fewer molecules than an equal volume of liquid water. And because of this, that means the ice is then less dense, so it will float on the surface of the more dense liquid water, even though if you go to another molecule, in general, the solid form is more dense than the liquid form and sink. This makes water so unique. And it is this ice on top of a large body of water in the winter that also then insulates the water beneath it, which stops ponds, lakes, very slow-moving streams, things like that, from freezing solid and killing everything beneath the surface. Water is considered the solvent of life. And to understand this, we need to understand what it means to be a solvent, solution, or solute. Now, a solution is a liquid containing a uniform mixture of two or more substances. A solvent is the dissolving agent. In our particular case, we're looking at water as a solvent. And the solute is what gets dissolved. So if you're looking at salt water, the salt would be the solute because it is what is getting dissolved, and the solvent is the water. It is what is doing the dissolving. And then specifically, an aqueous solution is a solution where water is the solvent. Now, water holds this place as the solvent of life because of its unique structure. Because it is a polar compound, it does have that very weak positive-negative charge going on within a molecule. This means it can dissolve ionic compounds like salt. Water is such a unique solvent because it is that polar molecule, which means it has an area of positive charge and an area of negative charge, even though those charges are very weak compared to ionic compounds like sodium chloride salt. And the way it dissolves these ionic compounds is once they get wet, they're very unstable bonds, and they will freely break apart, allowing the negative areas of water molecules to surround the positive ions and the positive areas of water molecules to surround the negative ions. So effectively what you get is a glass full of water with individual positives and minuses floating around in it, although the overall charge will still be neutral. The polar molecules, like sugar on the other hand, can also dissolve in water. And this isn't done by breaking apart those molecules. This is done by the water effectively surrounding the polar parts of those molecules, which in sugar's case here, all those little OHs everywhere on the molecule is where water is going to be attracted because that is the polar part of that molecule. And now that we've talked about solvents and solutions, we need to address acids and bases. Now, I'm sure everyone's heard of acids as these crazy things that can dissolve whatever they touch. And yeah, in some cases that's true, but let's rein it back and find out what that means a little bit. Now, an acid is a substance that donates and subsequently increases the concentration of the H+ atoms in a solution. And a base is a substance that reduces the concentration of the H+ or donates the OH-. It's important to note that in some case a base is just something that can accept those H+. But when you get like sodium hydroxide, that is an ionic compound that is donating OH-, and then those OH- react with the H+ to make water. Here in the middle, we see what is known as the pH scale. And the pH scale is basically just a description of how basic or acidic something is. It does go from 0 to 14. However, if you do study chemistry or biochemistry more in depth, you learn that 0 and 14 are not the absolute ends to the scale. But that's not important for our purposes. I just think it's important to note because that's something that I was never introduced to until I did study biochemistry and chemistry. So in general, our blood, for example, is going to be around a 7.4. So it's around neutral. Neutral is 7, but it's a little bit on the basic side. Now, what that means is something is considered basic if it is more than 7 on the pH scale. So 7.1 through 14 is the basic side of the pH scale, and 6.9 all the way back down to 0 is the acidic side of the pH scale. And our blood is slightly basic. Now, we will die if our blood drops down too far. If it hangs out at 7 too long, it's lights out for us. But if it gets up to 7.8, same thing. So how can a body actually keep its pH in that perfect range, especially when there's other parts of our body that are very acidic, like our stomach? Our stomach acid sits somewhere around a 2 on the pH scale, just to give you guys a little bit of reference. We have what are known as buffers, and buffers are substances that minimize changes in the pH. And it's a little more complicated than just that. Basically, a buffer is either weakly acidic or weakly basic, and it just interacts with the excess, either H+ or OH- to help keep things perfect. And this is important because life is sensitive, and water, pure water, will just be that lovely little 7, because even though the water molecules can dissociate into H+ and OH-, it's still gonna be an equal balance if it is pure water. Here, I'm probably gonna hop on my soapbox a little bit because I see a lot of people like to buy what's known as alkaline water. And basically, that means it's a weakly basic water. And it's a scam because our body, those buffers, they are going to neutralize that alkaline water anyway. And it's just going to be basically a waste. Your body is already the perfect pH unless you have a specific medical condition that is altering that. Alkaline water does nothing. The advertising they do that says it makes your body less acidic is a lie. Just to let you know. Now, to end our little water journey today, we're gonna talk about a couple of connections to different fields of study. First, to highlight the acid and base stuff, we're going to talk a little bit about ocean acidification. And basically, the idea of that is as CO2 levels rise, the oceans are becoming more acidic because it's making carbonic acid. And as these acidic oceans are happening, the growth of shell-building animals and corals is slowing down because there's just not enough of the carbonate for them to bind to calcium to make those hard outer shells and the hard parts of the coral. And this can potentially cause further problems in those marine ecosystems down the line, since these shell animals and corals are towards the lower end of those food webs and form parts of the base of those ecosystems. So the other field that we're looking at when we're talking about water here today is an astrobiology perspective. Now, astrobiology is just a field of biologists that are basically looking for life on other planets. And when scientists are doing this, they're also searching for signs of water. Since water is so important to life on Earth, it is very likely that it will also be important to life on other planets. So it's likely that if there's signs of water on another planet, that is a good place to look for extraterrestrial life. All right, that's all I have for you for this lecture. A quick reminder that if you are interested and you want my PowerPoint slides, they are available in PDF format for free on my Patreon page. The link is in the description below. And a quick reminder that we did discuss some chemistry topics today. I am not a chemist, so I did not go as in-depth as possible into them. And also, I am following the book, so I only went as in-depth as the book went. All right, I will see you guys all next time. Thank you again for watching this video. Don't forget to like, comment, subscribe, and ring that bell if you would like to see more. And if you'd like to follow me on any of my other social medias, the links are down in the description below. Don't forget to check out thereptilegoth.com for all of my articles and blog posts. If you found any value in this video and you would like to help support the channel, please check out my Patreon page. That link is also in the description down below. And a special thanks goes out to my Diamond Dragon patron, Diane B. What you're doing is really helping me fund a dream here. I will see you guys all in the next one.